Yeah, thank you very much. Before I start, I would like to mention my collaborators in that work. These are Martin Ender and Rüdiger Westermann from the Computer Science Department at the TU in Munich. Katrin Padberg-Gehle and Christiane Schneider from the Mathematics Department in Lüneburg at the university. My long-year collaborator, Janet Scheel from Occidental College, Los Angeles. And most of the simulation work has been done by my postdoc, Ambrish Pandey, who really deserves a special credit in this work. So what is this all about? Well, in principle, what we will study are turbulent flows in very large aspect ratios. And you can see a snapshot of the velocity field, the view from the top here. It's a rather low Prandtl number flow. The Rayleigh number is moderate, and you see a very complex flow structure, basically a very chaotic tangle of field lines. And then you start to average with respect to time, and you recognize very regular patterns of the mean flow, which are reminiscent to what we all know quite well from the onset of convection. And these structures we will term turbulent superstructures in convection, and I'm going to talk about them, about the scales. I'm coming to this. This will all be done. So why are we interested in such things? Well, we know that in nature, turbulent flows very frequently appear in regular patterns. We have heard this morning already quite a bit about solar convection. Here again a picture of the solar granulation. And just for comparison, I'm adding here a little thumbnail figure which shows the Benard-Marangoni convection at the onset. So this is the well-known phenomenon since 116 years, well-known since Henri Benard. On the right-hand side, you see cloud streets. So there's a continental ice shield here. This is Siberia. Cold air moves across the warmer ocean, and then these very straight aligned cloud streets are formed. And this is very reminiscent to what we know from the onset of convection. Here is a picture at a Rayleigh number that is only slightly above the onset, where you still see these nicely aligned structures. The Rayleigh numbers are huge. The flows are highly turbulent, as you can see, and it holds for many Prandtl numbers. It holds for very low Prandtl numbers, as we have them in astrophysics, but it holds also for Prandtl numbers above unity. So a few questions come to our mind. The first one is, can we observe such patterns in the classical standard Rayleigh-Benard convection, which is the simplest convection flow? It's basically the paradigm to all these flows which I have just shown you on my last slide. If yes, are these patterns indeed relics from the onset of convection? So are these structures surviving in phase space and are still there and have some kind of dynamic relevance, although the system already moves, turns turbulent? What are the typical spatial and temporal scales of these patterns, and how do they depend on Rayleigh and Prandtl? How are these patterns and their formation related to what's going on in the boundary layers of the turbulent convection flow? Can we actually develop simplified models which put you in the bird's perspective? You try to forget about all these little tiny features of the turbulent flow, and you really want to have a effective dynamics of the large-scale behavior, and how important is their role for the turbulent transport in the system. So I'm going to talk mostly about three of those questions in the following. So we have done numerical simulations, comprehensive simulations covering 4 orders of magnitude in the Rayleigh number, and covering also 4 orders of magnitude in the Prandtl number. So we're going down to something which corresponds to convection in liquid sodium up to a Prandtl number of 70. And yeah, that has been a 1 year ongoing work on the largest supercomputers, which are currently available in Germany. So, good. Let me get back to the first slide. And here I show you the full snapshot once more, together with the temperature field. And you basically don't see a lot when you look at the velocity field. You see a kind of structure already when you look at the temperature field. Now we are applying the time averaging over an appropriate time, which I'm going to discuss what appropriate means. And then you see indeed these patterns here. And you also see that these fine contours are smeared out, but mostly the structure remains. So it is observable from these comparisons, velocity and temperature, that it looks like the temperature shows these structures better from snapshots. You basically don't see anything if you're looking at the velocity field. So, sorry? I'm going to talk about this as well. Sorry, I have to. Good. So let's first take a look at comparing the fluctuation levels of the total fields, of these mean patterns, and of these of that what remains. And you see that basically the fluctuation level for the temperature field for all these Prandtl numbers, and also at a fixed Prandtl number for all these Rayleigh numbers, comes very close to the total fields. It's completely different in the velocity case. So this is the vertical velocity component. And you see basically that these structures, these roll patterns, are covered by the fluctuations. The fluctuation level is larger. So this phenomenon can be observed for basically all Prandtl numbers which we have looked at. You see it here, 10 to 5, 5 times 10 to minus 3, 2 times 10 to minus 2, 0.7 and 7, and also 70, which I'm not going to show here. And if you go at a fixed, if you go at a, this one. If you go at a fixed Prandtl number up the Rayleigh number from 10,000 to 100,000 to 1 million to 10 million, you also recognize all these patterns. So what are the typical scales with respect to time and space, and how do they depend on Rayleigh and Prandtl? Before I get into this, I'm just saying a few words about the scale separation. That's basically what we are trying to do. We are trying to get rid of the small scale features in the convective turbulence, which you see in the left figure. We're basically trying to smear out all the information across a scale lambda that we have to define later, and we are doing an averaging over a time scale tau. So we are basically trying to separate the fast, small scale dynamics from the slow, large scale dynamics in the system. And we will do this in the following by applying these kind of coarse graining with respect to time. So now I'm coming to the time scales and hope to answer Srini's questions. What are the time scales which we have in our system? Well, there's the freefall time scale, which is a rather short time scale. There are even shorter time scales if you move further down to smaller scales. But on the level of the height of the convection layer, the freefall time scale is one relevant time. And then on the other end, you have the diffusive processes, and you have a diffusion time, which is given here as the product of Rayleigh times Prandtl times TF, or you have the viscous time scale, which is given in a very similar way. And if you're now putting these time scales together, you see that there is quite a gap between the freefall time and these dissipative time scales. And so we expect that our coarse graining time scale, our typical time scale, is somewhere between the freefall time scale and the maximum of these dissipative time scales, which certainly depend on the Prandtl number. So which of these two is slower? So let's first take a look how things change if you are taking a snapshot just one snapshot, and then you are starting to increase the averaging time interval about the snapshot in the way as I'm showing it here. And you see with the time, with increasing time, you are removing more and more of these small scale structures from the temperature, and the velocity structures show up better and better, the roll patterns. If you're doing this too long, you start to wash out the information of the large scale structure. That is clear if you're waiting, if you are doing this averaging on time scales which are larger than the horizontal diffusion time, you are basically washing away this whole pattern. So the time scale is somewhere here in between, and in this sketch I'm trying to make, to bring up a kind of physical picture, what would be an appropriate time scale. We are observing these kind of structures in our system. We have these circulation rolls that have a certain wavelengths, which roughly agrees between those for the velocity and the temperature field. And we have a height, so that defines a kind of ellipsoidal shape on average for these rolls. And that gives you a length scale which a fluid parcel needs to turn over once or a few times inside such a circulation structure. The typical advecting velocity we take for simplicity just the globally determined root mean square velocity in our system. So one thing is missing. We actually need that scale here. We know the height, but we don't know that pattern scale. And that answers hopefully the second question. So we have to determine this, and we have done it in several ways. So one way is you are looking at the correlations of the fields, the spatial correlations in the two horizontal directions, or you are converting this whole midplane information, which we usually have taken into a spectrum, which you see here for the velocity and for the temperature field. And then the typical wave number is the one which is the one where this spectrum has a pronounced maximum. That can be converted into such a wavelength scale. And then you start to analyze this for all the flows that we have. Here is the Rayleigh number dependence of that typical roll diameter, so to say, as a function of the Rayleigh number. This is the critical wavelengths at the onset of convection, so that cannot be negotiated. This is the almost 2 at 1708, and then it starts slowly to increase, as you can see here. Up to 10 to 7, at least we see here a systematic increase of that scale. The Prandtl number dependence is a little bit more complex, as you can see here. It looks like it saturates for the very low Prandtl numbers, and then it increases, it goes through such a maximum, and then it falls off again if you're going to higher Prandtl numbers. At least this kind of behavior here has been also observed by other people, for instance, Thomas Hartleb, Andreas Tilgner, and Fritz Busse in some simulations. So we have extended that to the low Prandtl number end here in this system. Once you have these scales, you can calculate the time scale, and that seems to be rather robustly varying with the Rayleigh number. There's not much change here, and there's a slight increase with the Prandtl number. Okay, so the slow temporal evolution, now we recall ourselves what people have done in pattern formation many years ago, and there are, for instance, studies by Bob Ecke on that. So you basically now take the other part of the spectrum, you are averaging radially, and you are looking at the azimuthal dependence of your spectrum. This is exactly this quantity here for the temperature field taken. And there you see that there are maxima here, but there are also ongoing and offgoing side maxima here in parts. Here is the Prandtl number variation. these maxima shift and drift. So that indicates that there is a slow variation in the system, and that that these structures evolve very, very gradually on scales which are larger than our coarse graining time scale tau. And it also tells us that there are characteristic orientations of the roles or of groups of roles which are intersected by some cross-roll modulations in our system. So currently we are trying, let's first recall where do we stand in terms of the Busse balloon. So the Busse balloon is basically this, this shaded area here for two Prandtl numbers. I have taken that picture from the review article of Cross and Hohenberg. And this is the onset of convection at the critical wave number of 3.11 and 1708 Rayleigh number. And then you start to vary the wave number, and then the straight rolls in an ideal convection system are affected by all kind of instabilities, cross-roll, skewed varicose, etc. And you see this is where we are at the moment with our simulations for these two numbers. So we are always significantly far outside from the Busse balloon, but for the future it would be probably interesting to really go back to the Busse balloon and start from the Busse balloon surface to our points, and that gives us an idea, hopefully have an idea of where these patterns come from. We also try to connect the structures that we observe in the midplane to things that are going on in the boundary layers. So this is a sequence of figures for the lowest Prandtl number, 5 × 10⁻³ and this is for Prandtl number of 7. You see the temperature derivative at the bottom, at the plate, in these two figures, at the top plate in these two figures. Then we magnify these figures. These are these four figures which you see here, and we lay over the field lines of the skin friction field. That is, these are the two components that survive from the velocity gradient tensor at the plate, and they form a divergent two-dimensional vector field which has critical points, and these can be analyzed. And I want to point your attention now to the following fact. In the middle, we show the temperature field in the midplane. It's the same size as, so these three figures have the same size. And then you can clearly see that the plume ridges, which are formed at the bottom, show up as temperature maxima in the midplane. The same holds for the minima, for the cold stuff, which is falling down, for the hot stuff, which is rising. You see it much more pronounced for the low Prandtl number because the level of velocity fluctuations is, for the high Prandtl number, sorry, because the level of velocity fluctuations is much lower. So these are the line-like structures which we have discussed yesterday already in Jayvant Arakeri's lecture. So you can go a little bit closer and you can actually connect what's going on in the plates. Here's a magnification again. These are all the critical points. So these are saddles, nodes, foci. We have analyzed all of them. Quite a few, a very complex structure. It's much more simpler in case of the high Prandtl number case, where there are clear impact regions, and then there's a coherent flow pattern to the plume ridges here, which are basically manifolds of the saddles and the nodes. The field which is interesting somehow is the divergence of that vector field. So basically, the field that describes the sources and the sinks of these flow structures, and it is much more fine scale as here in the lower picture. So what we did is we basically calculated the spectra of all these fields. So the divergence of the skin friction field, the spectrum of the derivative at the plate, and the spectrum of the temperature field, and these spectra are shifted that they are better visible. But what you see nicely is that the maxima at which these spectra peak coincide quite well with each other, which tells us that there is at least a strong connection between what's going on at the boundary layers in terms of the plume formation and what we observe when we are coarse graining and look at the turbulent fields, for instance, in the midplane. We also have looked at the defects of these patterns. That's pretty hard, it turns out. We were at the beginning quite optimistic, but there's still some work to be done. When you just close your eyes a little bit, you see clearly that there are these defect patterns. And the idea is that actually this defect and this annihilation and formation of these defects is a kind of key ingredient to understand the formation of these patterns and their dynamics. So we have basically done, applied the machinery which is well known from many other fields, and it turned out it is only successfully partly, although these figures look very nice, there's still some work to be done in that respect. We have also tried other things which basically are really hardcore image processing, which our computer science colleagues did. So you take such a picture, you apply a Gaussian filter, you calculate a Hessian matrix of the intensity, you take the negative eigenvalues of this Hessian, you get a binary figure, which you see here, you thin out these maxima, then you get this, you start to connect these ridges which are missing here. You're doing the same stuff for the valleys and the ridges. So this is this figure here. I'm pointing with my pointer to the blackboard now. So the ridge is basically a hot region where we have upwelling fluid, and the valley, the dark region in the grayscale is where we have descending fluid. And then you can do an image segmentation, and you basically can divide your extended plane into segments where you have these rolls and these modulations across the rolls, and then you can study the transport in that system, which we have done, but there's still some work to be done. So the last part of my talk, in the last 7 minutes, I'm going to say a few words about a third way of analyzing these structures, which is basically the pure Lagrangian way to do it. So this is an old animation of Lagrangian tracers in a convection flow where we have colored the tracer particles with respect to their local temperature, and you can see nicely the plume structures and the falling and the rising plumes here. And so what can we do in respect to the large-scale patterns in the flow? So basically, when you usually look at Lagrangian studies, then people are interested in single tracers. They are interested in pairs or in tetraeders of particles that probe the local flow properties. Here, we actually want to understand the dynamics of the whole tracer ensemble, and we want to connect this to the structures. So this is a figure which displays the Lagrangian evolution. I have colored the tracers in red, which basically contribute locally very strongly to the heat transport. All particles started at a carpet very close to the bottom plate, and then with the time these tracers raise, there is a separation at the top plate, and then they turn around in these structures. And while we are advecting these tracers, we are simultaneously coarse graining the temperature field, which is shown here. So you see how the contours are smeared out. And the point is now, can we connect these things? So can we classify these structures, these roll patterns, as I used to say, with these clusters of the tracers? And one way to do that is applying graph theory. So you basically consider your Lagrangian tracer ensemble as a space-time graph, which is composed of vertices, edges, and weights on the edges. I have just given you a sketch here. And you're doing this with respect to space and time. And you are defining a kind of dynamic distance, which basically tells you how close two particle trajectories come on average over a certain time interval, which is t1 in this case. And then you are defining a weight, which is basically the inverse of this dynamical distance. So when they come very close, the weight is very high. When they move very far away, this distance becomes large, and then you have a very small weight, which you basically effectively set at some stage to 0. So the task is then the following: to cut such a graph into pieces by just removing a few edges. And that's a typical problem from image analysis. And there has been a landmark work by Xi and Malik in the year 2000, where they basically showed that this balanced cut problem can be transformed into a generalized eigenvalue problem for the graph Laplacian. So what you are basically do is you are constructing a graph Laplacian out of your tracer information, and you are doing this generalized eigenvalue analysis. What you would like to see in such an eigenvalue analysis is a spectral gap. And indeed, here are the eigenvalues. There is a spectral gap here, and that spectral gap gives you an indication how many clusters you can expect in your flow. And then you can apply a k-means clustering, and that is exactly what you get. So you see, in principle, you can reproduce the structural information which you see here from this Eulerian picture by a fully Lagrangian analysis in the spirit of this graph theory. I said already that you need to cut or you need to set your weights at some level to 0. That means you need some kind of physical scale which you apply to do this operation. And this scale should be somewhere between the boundary layer thickness and the scale which we have analyzed before in our analysis, Eulerian analysis. So here you see that's the way we analyzed convection in the past, by just having a kind of distribution of these local boundary layer scales, and that gives you an indication where your epsilon has to be in terms of a scale. Okay, good. That brings me to the summary. I have shown you that large-scale patterns are detected in turbulent Rayleigh-Benard convection for all Rayleigh and Prandtl numbers once we remove the fast small-scale fluctuations, and we term these structures superstructures. They have a characteristic scale, which basically is something like the diameter of the circulation row, the horizontal diameter, and this depends on Rayleigh and Prandtl, as we have seen. We have also seen that these patterns evolve gradually on time scales, which are significantly larger than the free-fall time scale. We're talking about something like 60 free-fall time scales, roughly, or even more. But they are still much smaller than the diffusion time. So that gives you at least a range of scales how you can divide the small, fast, and the slow, large-scale motion. We have shown that these patterns are connected to the formation processes in the boundary layer, to the plume formation, to the plume clustering in the boundary layers, and they can somehow brought into relation with the skin friction field, which is a nice blueprint of what's going on in terms of the advection of the temperature field near the plates. you can try to, we are working on that, you can try to reduce these structures basically to the connection and reconnection of these topological point defects that hopefully gives you an effective way to describe the dynamics. And we have also seen that you can go into the Lagrangian framework and reveal these structures again. And with that, I want to thank you for your attention, and yeah, I conclude. Yes. Yes.
Considerable averaging.
Yes.
By the way, I'm a fan of your work on this. You know that already. How do they compare with the structures that you see just past the critical Rayleigh number in scale, if not exactly in the form?
They are larger. They are always, so they are extent. That means the typical scale grows, the wavelengths growth. And that is probably due to, I mean, the picture I have in mind is if you have a roll at the onset of convection, it has a very canonical wave number, and then you have all kind of oscillations, instabilities between these rolls, and that effectively causes a growth of these.
We know the critical Rayleigh number does change with the critical wave number does change with the Rayleigh number around the critical Rayleigh number itself.
Well, at the onset, it's all the same.
Well, I mean,
a little bit.
It does, yeah,
yes.
Yeah.
Then it's.
Okay, so
that's basically this picture, which
all right.
Probably should go back to the Busse balloon.
No, it's. I know you showed it. Showed the where you are.
Yeah. Yeah. Yeah, it looks like that these scales with increasing Rayleigh, that's a trend which we see for all of them. They go to the left. So smaller wave numbers, larger wavelengths.
Hello? Sir?
Okay. Joerg, you have shown these beautiful patterns and everything, and that they are really stable. And I would like to ask you, I mean, how do they fit together with the mean wind? So you need
well, the mean wind is basically what's going on in one of these rolls. If you have a gamma-1 cell, that is
the gamma-1 cell, we have the small patterns and we have no mean wind altogether.
Yes.
So
yes, and here it's gamma-25. So you basically have 25 gamma-1 cells, or a little bit less. So what we know as the mean wind in a laboratory gamma-1 cell is here probably what's going on inside one of these rolls.
Okay, thank you.
Yes?
Sir, in the times you show, the table of times, there was one TG and a constant value. What is that?
Yeah, that is, Keith Julian asked me what is the geometric mean between these two scales, and that's exactly constant. I don't know if that helps us. Let me go, I think I need to, you mean the last column, this one, right? This is the geometric mean of these two time scales. Yeah, so there was the idea if that is the right time scale to take, but I think the time scales are still a little bit smaller. They come close to that, but that was just for fun. So far I don't have a clear recipe if that time scale helps somehow.
So Joerg,
yeah.
Go ahead.
You referred to some equations that have been derived in the literature for describing the slow evolution of these patterns.
Yes.
Presumably in the simulations, these patterns also change over time.
Yes, they do.
And have you tried to figure out parameters for these equations?
A very good question. The problem, although the Rayleigh-Benard convection flow is so extremely simple, it is actually much harder to do that. And the reason is we don't have an additional physical process which constrains the dynamics. So people have done this, for instance, for rapidly rotating convection or for convection with a strong vertical magnetic field. You can go for a really mathematically firm asymptotic expansion then, and you can derive a reduced set of PDEs, which has been done. Keith Julian, Edgar Knobloch, and co-workers. In this case, and I have been talking with these colleagues a lot, it's hard to do that. So we always need a kind of hand-waving arguments. The way we are now trying to proceed is basically that we are looking at the small-scale gradients and trying to compose some kind of turbulent viscosities and diffusivities. So basically, at the beginning, a kind of classical Runz type or Smagorinsky type approach to that. Yeah, unfortunately, a rigorous mathematical pathway seems not to be possible.
Okay. So,
I think Mahendra, yeah, oh, sorry.
the spectrum, do you have plot of spectrum? One of the plot with spectrum, no, which is EK. Did you look at?
Oh, we didn't look at the slopes. At the moment, we were just interested in the patterns. Yeah, we certainly can do that. Yeah, the data are there.
Can I ask a question?
Yes.
So is there an a priori reason to believe there will be strong correlation between the patterns in the temperature field and the Lagrangian tracer patterns?
You refer to the connection between the boundary layer and the midplane, or in general?
You said there are correlations between your results from graph theory used on the Lagrangian tracer patterns and the structures in the temperature field. But is there a reason?
Well, yeah. Well, it's the tracers are advected by the flow structures. The flow structures are coupled to the temperature structures, right? In this way. And I mean, there's a tricky part in the Lagrangian analysis, which gives us currently still a hard time. I didn't say that, but I can say it now. I mean, you always have to fight against the turbulent dispersion. So you would like to have those tracers for your graph analysis, which basically get trapped for a long time here. You don't want necessarily those guys who separate exponentially fast here when they are hitting the top plate and basically go into a hyperbolic region. Yeah, so it's there's still some space for improvement, but otherwise, I think the connection is just that. Yeah, these tracers follow ideally the flow structures, and they are tight. The scales, as you have seen, are always very close between temperature and velocity.
Can you go back to the first slide?
Yes. Yeah. Oh no, sorry. This one.
So this is one of the instantaneous.
Yes. 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 It's basically this figure. This one. The same, just a little bit bigger. So it's the same data.
Could you really pick out these patterns somewhere without the aid of naked eye?
Well, you can somehow here, right?
Here you can, but there
it's harder. And it depends on the Prandtl number. I mean, we have only, when you have very high Rayleigh numbers or when you have very low Prandtl numbers, it's going to be pretty hard because you have this vigorous fluid turbulence. And then it's probably not so easy to do that. You mean from instantaneous snapshots? Yes?
Transform may help.
Yeah, we did. You mean from the instantaneous? Yeah, well, yeah, we did this. So you take an instantaneous snapshot, you Fourier transform, you cut away the high wave numbers. Yeah, yes, in principle, you could do that as well. Yeah. But what we want what we would like to have is a time scale and a spatial scale, right? I agree. It's another way to do that. Yeah.
Okay, let's thank the speaker for the nice talk.